Let's recover the example of the distant star system of one planet revolving the star. Because they are far away from other external forces, we are going to consider this as an isolated system. If that's the case, the total momentum of the system is conserved. Writing Newton's second law, we have that m1 times v1 dot is equal to f12 and m2 times v2 dot is equal to f21, which using Newton's third law is combined as f12 equal to minus f21 and 1v1 dot plus m2v2 dot equal to 0, or the derivative of m1v1 plus m2v2 is equal to 0, which is just the conservation of the total momentum of this physical system. It seems that momentum is just the velocity multiplied by a number, the mass of the particle, but it's more than that. The velocity of the system is not conserved. We can solve v2 and write it in terms of v1. Then we can calculate the rate of change of v1 plus v2, and we see that this is not a conserved quantity. It can change in complicated ways, but not momentum. That's why momentum is special. Conserved quantities are cool. Imagine you want to measure the height of a building. With your knowledge in physics, you decide to go up to the roof of the building, drop a baseball, and measure the time it takes the ball to reach the floor. The forces acting on the ball, if we neglect frictions, are its weight, and that's all. So Newton's second law reads mx2 dots equals to minus mg, where we consider positive going up. This is a differential equation that you can solve and find as solution that x of t is equals to h plus v naught t minus 1/2 of g times t squared, where v naught is the positive if you throw the ball up and negative if you throw it downward. That's the equation of motion, which gives the position as a function of time. What if what you're interested in is in the velocity of the baseball when it reaches the floor? We can here opt to use conservation of energy. Kinetic plus gravitational potential energy is conserved. mgh plus 1/2 of mv naught squared equals to 0 plus 1/2 of mv final squared. From here you solve for the final velocity and get that v final is the square root of 2gh plus v naught squared. We found the answer without solving any differential equation or considering any forces. Here the role of the force is implicit in the potential energy, and the role of the kinematic quantities of motion related to acceleration are implicit in the kinetic energy. What if what you are interested is in the velocity of the baseball for any given height x? Again, from conservation of energy, we have mgh plus 1/2 mv naught squared equal to mgx now plus 1/2 of mv squared. Solving for the velocity v is equal to a square root of 2gh minus x plus v naught squared. Well, this is another differential equation, as the velocity v is x dot, the derivative of x with respect to time. If we integrate this equation, we get the time of flight of the baseball, square root of 2 over gh minus x plus v naught squared over g squared minus v naught over g. What we've been presented in these last two videos is something we're going to be using consistently in this analytical mechanics course. We'll eliminate forces of constraint, we'll exploit the suitable coordinates, and we'll stress energy and conserved quantities.